Vanesa is a leading light in the world of quantum communication, full of valuable insights on the quantum revolution. She's the CEO of LuxQuanta, as I said, one of Europe's leading continuous variable quantum key distribution, CVQKD, manufacturers. Vanesa, good morning. Okay, just make sure that we have the sound.
Good morning.
Hey, good morning, Vanesa.
Good morning, everybody.
I'd like to introduce you to the audience. I can see that you can see us in the room, right?
Right, so the audio is not great. So if you can maybe right there or come closer than
okay, Vanesa, can you hear me like that?
As soon as we... Yeah.
Vanesa, I leave the floor to you to go ahead with your presentation.
All right.
Go ahead. Thank you.
Thank you. Thank you very much. Right, I'm going to share my screen. First of all, it's a pleasure being here with all of you today. We prepared a presentation from LuxQuanta that walks you through very high level about the quantum cryptography, the status of the technology, what in particular we are doing in LuxQuanta, but trying to keep this high level view on the different options that are out there. And then we're going to narrate down on the different verticals that we are seeing out there in the market that are embracing this type of solution to protect their communications. To close on a conclusion, no? on a wrap up. So this is very exciting times. Quantum cryptography is a technology that have been incubated in ICFO. This is a little hints or not about who we are and where we come from. So LuxQuanta is a spin-off. We are now 2 years old. We were born in May 2021. We were born from a research center in Barcelona. They work with photonic sciences, and whenever they find a technology that is very disruptive, which is the case of quantum cryptography or quantum key distribution, they release a company. So we are number 10. But the truth is that the project has been incubated for over 4 years, and that's the reason why I'm sitting here with you today talking about a pretty advanced status on the work that we've been doing. What we inherited from this research center, ICFO, it's a type of quantum cryptography called continuous variable. So we're going to look at what this means and how it's complementary to the technology, quantum key distribution technology that we have in the market out there. So we are already 22 people, and our shareholders, you might recognize some of them. Courtney is where I actually come from. I'm a telecommunication engineer that decided that her passion was more in the commercial and the strategy arena than in the engineering side of the story. And then GTD, it's a company that works with software for mission critical systems. So it's been 2 terrific years for us. We've been even awarded a couple of times. The first 2 of many, we hope. And the work has been busy because the world is recognizing that there is an increased threat in terms of the security of our cryptography. So for those in the audience that might not be familiarized with this, when we talk about public cryptography, we are referring to that key that we use to encrypt the information that somehow needs to be agreed upon so we can hide somehow the communications afterwards. So the most secure way is symmetric cryptography. So ideally, we would get together physically in a place where we'll agree on a key, and then we would just go to our own locations, and we will be using that key that we agreed to encrypt the information. But we live in the era of the internet, so we cannot get together to talk to, through WhatsApp, just to put a very simple example. So we'll use asymmetric cryptography, and this is what this metaphor is going to explain. Asymmetric cryptography means that one part of the link is holding 2 keys. The public key is the lock that we send open to the other side of the link, that we want to privately speak to, and that other side sends the information back protected with that lock. So the only one that can actually open it is ourselves, because we are the only ones who have the private key. But this metaphor is great because if you think about a lock and a key, the reality is that if you look correctly, if you do your job looking at the lock itself, you can extract the private key. And this is that protection or that way of reversing, doing this reverse engineering in this public cryptography that we use today is undoing a mathematical problem. So one of the algorithms that we use the most, called RSA, is based on the factoring of prime numbers. So if you have enough computational capacity to factor the prime numbers that are somehow hidden, no, in that result of the multiplication in the lock, you could potentially get the key. So far, we've been strengthening our cryptography. So we've been making the prime numbers larger and making things more and more difficult, because at the end, we depend on how strong our adversary is in terms of computational capacity. Hence, one potential direction not to keep strengthening our cryptography is to keep thinking about even harder to solve mathematical problems. So when we go outside and we hear post-quantum cryptography, PQC, this means harder to solve mathematical problems, which definitely they have an application, and there is a big push from NIST, that's the security agency in North America. They are finding those algorithms that will be really hard to hack. But at the end, even in the contest, not to get to those final algorithms, there's been people that have been proposing their own that have been hacked over a weekend with a standard computer, saying that mathematical people out there might know about some algorithm that could potentially hack this new fancy way of protecting the information. This doesn't mean that this solution is not valid. It means that it does definitely have an application space. But I think it's good looking at the amount of delicate information that we transmit around the world to have a plan B. So the risk, because probably in the audience, if you weren't aware of this, the question is, well, why would we threaten, in terms of power cryptography? We have quantum computers around the corner. The around the corner is very hard to narrow down. So some entities estimate that by 2030, we will have a quantum computer that is strong enough, which means they have enough qubits, so they can truly have this capacity to do outstanding things, and therefore be able, among other things, to break our public cryptography. This is not a matter of if, it's a matter of when, because what we see is the world has embarked upon a frantic race to make sure that they achieve this quantum supremacy. So you can see pouring money from all the different governments around the world. So that's the reason why the perception of risk has been increasing over the last few years, and therefore there's been a more interest on understanding what tools do I have to make sure that my information is protected. So we could go in that direction previously discussed. We could make our mathematical problems harder to solve. But there is another approach that will never be dependent on how strong my adversary is, with the computing capacity that is holding. It is called quantum cryptography or quantum key distribution. The name is great because it already explains what it does. It distributes a key and it protects that distribution using the laws of quantum physics. So at the end, we're talking about a solution based on hardware, unlike what we saw before. Mathematical problems means software. In our case, this is hardware, and it means that we add another layer to the link that we are going to protect. We have two machines, often called as Alice and Bob. This is a common criteria in cryptography. And they are going to use transmission media, optical fiber, the air, to send the key coded in the form of the optical light. And they are going to send that information to build a key so attenuated that the laws of quantum physics will take control. And in that universe, there is one law that says that if you observe a particle in the quantum realm, you affect it. So basically, this means that I'm going to send the key through this standard channel, but so weak, relying so much in the laws of quantum physics that if there is an observer, I'll be able to tell. So at the end, all quantum key distribution does is creating a very secure channel, so I can exchange a key. So both sides of the link will end up having asymmetric key, which is the most secure of all the possible cryptographic keys you could have. And then the communication is going to be encrypted as usual. Now, this technology is not new per se, so it's been gaining a lot of attention over the last few years, again, because this perception of fear has been increasing. So if you look at the estimations out there on how big this market could be, one that we like a lot is from Inside Quantum Technologies. They consider by the end of this decade, we could see over $5 billion in revenue moved around the world, just only around quantum key distribution. The reason for these huge expectations is because at the end, there are a lot of entities that could potentially benefit from this truly future-proof protection for their communications, ranging from governments, hospitals, banks, telco operators, critical infrastructures, even cloud service providers, not only data center, but cloud service providers. So that's the reason why there is a big push out there from governmental to private industries as well to understand the technologies, define a roadmap, and start thinking about where, no, in the network, it makes more sense to deploy which one. So let's talk about which one. There are two technologies in terms of quantum key distribution that are the most mature that we can literally buy out there. The first one, for us, is the traditional approach. It's called discrete variable quantum key distribution. And what it does is, again, we are coding the information of the key in this case, in a property of the photons. So it works almost like looking at each individual photon working on the spin, no? To code the 0 or the 1 that is carrying the information from the key. So here you will hear a lot of the protocols, no? BD84, BD92. This means which criteria we use to code the key in those photons. This is forcing me to have in the receiver a single photon detector, and this is a machine that is a bit delicate, meaning it's not great tolerating noise in the adjacent channels in the same optical fiber, no, in the same band. So this means that in the optical fiber, I have colors that I can use like in a highway, different lines, no? So I can go with the car. So if you have the quantum channel, meaning the part of the color of the optical fiber that I'm going to use to establish the key, I cannot have in the channels nearby, I cannot have the data being transmitted because the single photon detector will not work well. So that's why these manufacturers often say to you, push the data somewhere else, or put my quantum channel in a specific part of the optical fiber, and then off we go, no? Or empty the optical fiber entirely for me so I can work properly. The good thing about this technology, though, is that is achieving very long distances. So right now, the manufacturers, they are working on the 120, even 150 kilometers maximum distance. So the co-propagation is the one thing, though, that is not that great. On the contrary, continuous variable QKD, this is the technology that we work with. We are literally, you can count the manufacturers on this new flavor or version with your one hand. So we are very little of us, whereas in the other side you have dozens. So in this case, we code the key using not the photons, just the entire optical wave. So we're coding the information the same way we do in the telecommunication industry, not modifying the amplitude and the phase of that optical signal. And then I attenuate it very much. So again, it starts behaving as per the laws of quantum physics. So I'll be able to tell if somebody is sneaking into the channel. So the principle is the same. But because I'm doing things completely different now, in the receiver, I can have a coherent detector, which means that I have a local oscillator that is pumping that specific color of the light where I'm sending the information to build the key. And this allows me to have a lot of data being transmitted in the colors nearby. So co-propagation is one of the things that this new flavor technology is making it very special, no? And the other thing is that the components that we use are all very mature for the telecommunication industry, where the performances are very stable, so we can tolerate a wider range of temperatures. So at the end, these two technologies, we like to say, and we are reading the industrial manufacturers that are very much complementary because we are limited right now in the maximum distance that we achieve. So we're working around 40, 50 kilometers, no? So we like to say that continuous variable makes a lot of sense if you're thinking about a metropolitan or intra-city type of communication where you don't have the luxury of pulling new optical fibers to connect each customer. So you have to make sure that the data and the quantum channel coexist. So if you have a bank, for example, with the data center, and they already have an optical link connection both, you can install Alice and Bob in both sides of the link and then use one of the colors of the light to establish the cryptographic key, and that'll be it. Whereas if you think about discrete variable QKD, this solution is great when you need to go for longer distances. Different benefits, different applications, complementary technologies, both extremely useful now. The way that we position continuous variable though is to be this super easy to install type of technology. So if we had to highlight what makes continuous variable very special, is this ability to be easily deployed. Sorry, there we go. So this co-propagation, so we can coexist with data in the same optical band even, and we have the potential to deliver a technology that is zero touch, meaning extremely easy to insert in an existing optical network. In terms of performance, it's very reliable because the temperature range that we tolerate is similar to in the telecom industry. So there are some environments like a central office, for example, where temperatures can go as high as 40 degrees and even beyond. So it's very important that the system is very reliable. And in terms of key generation, because at the end, Alice and Bob, all they do is just constantly generating keys, and you need this key rate, ratio to be as constant and as high as possible. Continuous variable is great to do that and be very reliable in these intra-city type of links. Last but not least, one thing that really concerns me personally is that if the market really ramps up as promised, we are going to have to deliver thousands of quantum key distribution systems around the world. So we need to be able, all manufacturers, to mass produce. So for us, this means going into all the layer. I'll show you in a minute. All the optical layer that right now we are buying off the shelf, collapse all that into photonic chips, and that will allow us not only to be a lot more aggressive in terms of pricing, which is going to be beneficial from the industry, but also to enable mass production. So this is what LuxQuanta did this year, and the work that we are doing right now with Mercury and in this project in Prism. It has to do with this first system that we released called Nova LQ. This was released in February this year. We became the first European manufacturer to release this technology that has already been tested by local governments, the European Commission, and some other research institutes. It's called Nova LQ, but this is just the first step because, as introduced before, for us, it's very critical that we make sure we have a flavor of this technology with a photonic integrated chip in it. And because that's gonna, in a couple of years' time, 2-3 years' time, it's gonna allow this market to really flourish. So I'd like to explain a bit what this means when I say, as I anticipated before. So what does it mean when I say that we're gonna have a photonic integrated version? So this is again another schematic on how the technology, quantum key distribution, looks like in general for any manufacturer, but with a bit of a focus on ours technology. But it's kind of similar. So you have at both sides of the link, once again, Alice and Bob, and what you see are the applications at the very high level. This is very important because we've got this question many times. So we are agnostic to the applications. The applications are in need, or are eating keys. And all we need to make sure is that we're constantly generating those keys and passing them up to the next upper level. So the system, one side of the system, in this case, Alice, we will always have 3 layers. There will be always an optical hardware layer where you have all the components that literally build the optical signal. Then you have a signal processing layer that's going to create the quantum signals, and most important, in the other side of the link, is going to extract the quantum signal from the noise. And then the highest layer, that is the one that communicates with other machines, the applications, the cryptors. It is also the layer that is gossiping to the other side of the system, and it's also doing this reconciliation, this key reconciliation. So you will always have this, let's say, 3 channels, but this is the beauty of continuous variable. You can collapse them all in one single optical fiber. So you will always have this quantum channel. That's the channel where we're gonna safely share the cryptographic key. And that layer in both sides of the technology is what we will collapse in a transmitter photonic integrated chip and a receiver photonic integrated chip. And then the layers above, you have the software one. That's the one that is going to, just using a standard wavelength in the optical fibers, talk about agreeing on the key. So it's a process that takes some time. So you send a burst of information using the quantum channel to the other side, but then there is a lot of Alice and Bob gossiping that needs to take place to agree together on a key, and then they will pass to the applications above. So those applications, then they can encrypt the information, business as usual, So again, all these 3 channels, at least in our case, with continuous variable QKD, can be collapsed in one single fiber. So this is the beauty of what we do. So the technology that we released, Nova LQ, is already in the boxes on that vision I introduced to you before on the technology. So it's already easy to install because it allows this good propagation. It's already delivering an excellent range of operation. and the key generation is around 40 kilobits per second. Remember that these technologies are always conditioned to the separation between Alice and Bob, no? The maximum distance that you have. They are very delicate, so at the end, actually you cannot have any amplifier in between because you kill the quantum magic. And so the further away that you are, the lower the key rate that you are generating. So when we say 40 kilobits per second, is in the best, in a really good scenario, no? Now the system already has, and this is something that all manufacturers will offer to you. So this is not, it's not for your knowledge, not to pitch the system. So they will always have a system, metrology and telemetry, so you can have a look at how the machine is operating inside, and if everything goes well. It has to enable different topologies. This is very important because in all this time I've been always picturing a point-to-point link, but there are other configurations very interesting that can even make the deployment cheaper. For example, that star topology where you have one Alice in the center and multiple Bobs around. So that's one of the proposals that we are doing for a set of hospitals. And it can actually save you, I think it's like 40% of the total cost, no, in terms of this hardware investment. Inside of these machines, I've always been saying that this technology is carrying the key, but the key has to be generated somewhere. And ideally, the best is to have a quantum source of entropy, no? So you make sure that there are absolutely no patterns when you build that key. So in all quantum key distribution solution, you will always have a QRNG living inside. So in our case, our quantum random number generator is coming from QSight. They are a sister company. They were born from the same research center where we did as well. And then last but not least, this is very important as well. So when you acquire some of these systems, they cannot exist on their own. It's the same as in life. You need friends and family. You need the machines to be able to talk to the encryptors that they will be passing the keys to, or the famous key management systems that Andrea probably will mention later on. And what they do is just coordinate. If you have several point-to-point links, they help you. These machines, they help you look at all the different keys that you need, so you can do hop on, hop off, and go across the entire city or the entire country. So that interoperability is very critical, and there are some organizations, standard organizations that are in more ahead of the game. We'll have a look at this in a minute. So it's often that you hear about ETSI. ETSI is one of the standard organizations that is proposing ETSI 4 and 14 for this inter-machine communication. So that's something that the manufacturer has to offer. And then last but not least, for this point-to-point connection, they should have a KMS inside that allows for that very simple communication. Again, not as fancy as the other level, no, above. I wanted to mention something very important as well, because this is, I think that you leave this talk with a good sense and grasp on what's going on in the quantum key distribution industry is important. One of the verticals that is showing big traction is the one that has to do with cloud service providers. So Amazon Web Services, we became the first manufacturer to show up in Amazon Web Service Marketplace, and we became the first partner in Europe to work with them. So there is a portion of the link when we think about the cloud, because we heard this a lot. It's like, why would I need QKD? No, if I am accessing the cloud and I have all there protected. The truth is that from the office of any entity to the cloud, and there is an optical link that is running through the entire city up to that data center, where the router from Amazon Cloud is there. So that public link is the one that quantum key distribution can protect, and this is the direction towards we're going with Amazon. And again, I think it's symptomatic of where the market is going, because when you go outside, you will hear a lot. Well, there is a lot of funding from the European Commission, and it's true. There is a pretty strong geopolitical race on making sure that this technology is born and bred within each region. China is going well ahead of the game in this regard, but the European Commission has been doing a wonderful job over the last few years, pouring money to make sure that not only they have manufacturers of QKD within Europe, but also there is a backbone network being deployed, and Andre will expand on that later, of quantum key distribution within each member state, but also interconnecting them. So this is the market, or the vertical that we like to call innovators, because they are the ones that are now pushing the hardest, with this EuroQCI deployment. So the European Commission earmarked around 600 million just only for QKD related projects. And in January this year, they allocated the first package to the European QKD manufacturers. So LuxQuanta was one of them. We create this consortium with Telefonica, Thales, some other entities that we call Quartet, and we received 7 million of public European money to make sure that our technology is going to meet in terms of readiness and security standards, the requirements of the European Commission for this very ambitious deployment. Actually, the biggest chunk of that funding is coming for us, no? But in parallel, also the European Commission was allocated money to each member state, up to 5 million, so they could co-fund the deployment of their own quantum key distribution network. So that's what's keeping us quite busy. So a big chunk of the sales that we are securing this year has to do with this deployment. But I wanted to mention something though before moving into this slide. Even though we're talking about European funding, I think it's worth highlighting that each consortium on each member state is assembled with companies from the private industry as well. So you see really strong telco operators, really strong telco houses that they have also invested their own money. Yes, they are taking the opportunity to now look at this technology because they have the support from the European Commission. But the perception we get after talking to so many of them is that the intention is to use this as a starting point so they can really embark upon finding a roadmap for deployment, assessing the technologies, and so on. So making sure that we are very well aligned with the industry is critical because we need to make sure that not only the technology is fit for purpose in terms of the European Commission, we need to make sure that at the standards level, everything is working well, no? So LuxQuanta is paying a lot of attention on joining forces with in any consortium that is going to allow this kind of synergy. So we're always open for collaboration. So I wanted to mention to you QSMP, so the QSM partnership is pretty large, so you will hear a lot about it. There are a lot of companies inside of that, and the idea is to look even beyond quantum key distribution into quantum communications. So again, it's very relevant to have this in mind. So I mentioned to you before, the system that we released in February this year was already tested with local governments, again, the innovators. So this was a pretty big event. We were protecting a video conference from a research institute, the one that we came from, and a building of the local government of Catalonia. But I think it's most important this one, and it's aligned with what we're discussing right now. So what's happening in terms of this vertical, no, governmental and public institutions. So the European Commission, through Petrus, that's a coordinated call that is helping all the European QKD manufacturers and all the different member states that are building their own network to coordinate. And this exercise that they assembled was excellent. It was executed in 2 different conferences, the Digital Assembly in Stockholm and ETTC in Hanover, literally last month. And it was about combining the strength of different quantum key distribution manufacturers in Europe. So you can see here the second version in Hanover. We literally showed up with our systems, no, in this conference. And we're combining our continuous variable QKD with the discrete variable of UTI and Shin Quantum. We are Italian startups. And then Jena, they are working as well with entanglement. It's another flavor. It's a little bit less mature. That's why I not often talk about it, but it's a lot of technology that is in the pipeline. So this was excellent because they were also having a KMS, in this case was led by the University Polytechnic of Madrid. Rodersbach was as well. This shows the muscle, no? The importance of this, because we have pretty large corporations getting involved. Rodersbach was putting forward their encryptors, and Telsi was the one coding the application, the video application that allowed to illustrate how the system works somehow. So just as a note here, I like to say the things that worked the best were actually the QKD systems, which I think it was excellent. Right, so standardization is gaining momentum. I like you to leave as well this talk with a clear idea in mind about this world. So the best way is to show you how standardization works. At the end, when we think about any piece of hardware, we need to think about standardizing first the hardware itself. So when there is a bunch of standards out there, again, if you look at this list here, you will see Etsy as the one being mentioned the most, because it's the one that has been spending most of the time agreeing on a standard. But there is also, this is actually no longer a draft. So there is already a version from ISO organization, no, in this regard. So this type of protocols, what they say, or the standards, what they say is how the QKD module has to be assembled so it's secure. So the QKD manufacturers will need to keep an eye on them when we assemble our systems and when we design them. But the machines on their own are nothing. We've been saying this all the time. They need to talk to other machines. So interoperability is critical, and there is also a set of standards in this direction that are helping define that communication. So this is where you can see, you saw me mentioning this before, no? Interoperability, ETSI4, ETSI14. So these are the two most common ones. And then you will hear a lot about ETSI15 that has to do with software-defined networks. So the industry is already one step forward. We're preparing QKDs to be able to operate in a software-defined network type of environment. And then last but not least, right now, we are always, when we think about a very wide area covered by QKD links, what we have is literally the links one after the other. No? So eventually you are going to die in a bob and born in an Alice. And these two machines, they have to be back to back and protected if you want to have a system that is truly secure. So the Alice in Bob, make sure that the key is being transmitted safely between that optical fiber link. And they have to be, when they are collocated, they need to become a clustered node, meaning that there has to be some kind of vigilance and some kind of control. So there's another set of standards that are looking precisely into that. So what a trusted node looks like. And this is where you can see Etsy, but quite interesting, the ITUT is paying a lot of attention to this type of analysis as well. So they are well advanced in this regard. So that's it. Innovators covered. The rest of the market for us is the early adopters, telco, network providers, so the operators of the world. And then financial institutions, they are doing an outstanding job as well. We have a few demonstrations in the pipeline with one of the largest European banks, and also cloud service providers have already introduced to do this work. For this market, it's critical that the QKD manufacturers lower a bit the prices. Right now, they are a bit too expensive to think about a mass deployment. If you think about a telco operator that wants to really make the most of QKD, they need to deploy quantum key distribution links for the entire cities and across the entire country. So we need to make prices more affordable, and this is the reason why this photonic integrated conversion is very important. And it's the same for financial institutions, because they have hundreds of branches that they would ideally like to connect, not only just a specific one link between two emblematic buildings. And then the critical infrastructure and health centers, they are a bit the ones that are the latest, but there are very interesting things still going on in that regard that is symptomatic for a market that is ramping up as we speak. So that's it. We wanted to give you an overview of the technology and let you know that we exist. Again, we're a small company, but I think that as our foundations are solid, we have already released the technology that can help us start walking this path together, not to define a quantum secure network. We're very aware that it's not something that we can do overnight, so we need to work very close to each organization. Our solution is not the only one. We know that for sure as well. So there is PQC that needs to be considered, and that's something that when we approach any potential customer, we try to be as honest as we can on selecting the best technology that meets the challenge. And then last but not least, we like to be at the forefront of innovation. So any collaboration that you might have in mind will, for the short future, medium future, count on us, because we'd like to jump on board. So let's embrace the quantum era together. Make sure that if you need help, you talk to us. So thank you very much for your attention.
Thank you very much, Vanessa.